All right, so let's see what this central limit theorem is saying here. So it turns out that um, again, so it doesn't really matter what distribution that you're sampling from, as long as the distribution as long as the distribution has finite variance. So let's think like this: what's the age of a penny? It's pennies are probably what, about 25 years old on the average, maybe something like this. Um, and I would conjecture that maybe the ages on pennies are sort of have a right skewed distribution. That makes sense, right? Because the older they are, the more they tend to drop out of circulation. They get dropped in the lake, or collectors put them on a shelf or whatever. So let's take um, 10,000 pennies and record their ages here in column 1. With a mean of 25. Okay, so that's what I've got there, some ages of pennies, and we can take a look at that distribution if I make a histogram there. All right, so that's pretty good. I'm gonna make one slight adjustment there. I'm gonna um, start from 0, maybe go in increments of 3, something like that. Okie doke. And yeah, so this is not unreasonable. I think this sort of shape for the ages of pennies. By the way, we're sampling from an exponential distribution. I don't know if that's a really good fit or not for ages of pennies. It probably isn't. Okay, but anyway, so this is we're effectively taking samples of size 1 here, right? Now, let's do this. What if I decide that we're going to take samples of size 2? So I'll do this thing again. All right. So now I have, think of it like this. I took 2 pennies. These are the ages on my 2 pennies, about 8.7 years and 8.8 years and a little over 11 years. And then Brenda took 2 pennies, and here are the ages on her pennies. And then Kyle took 2 pennies, and here are the ages on his pennies. And so we had 10,000 people. See, 10,000 people each took 2 pennies. We're doing this 10,000 times because anytime you want to take a look at the behavior of something, you have to witness it a whole bunch of times to ascertain the behavior, right? And over here, I'm going to put the sample means. Okay, so I can do that by doing row statistics, right? Put all that stuff in column 3. So this is the average age of my pennies. Okay, this is the average age of I forget, Brenda's pennies, and this is the average age of Kyle's pennies. Let's take a look at the behavior then of the sample means by making a histogram. Aha! Now, what do you notice about that? Here's our original graph, and here is our unoriginal graph. Right? I'm going to put these on the same scale, by the way, so that we can make good comparisons. Let's say we make the minimum 0 and the maximum, let's say 200. It's probably good. And I'll do the same thing over here. Minimum 0, maximum 200. All right. And these are for samples of size 2, right? All right. So how are these different? Well, let's see. This one is rounder, right? Okay. The sample means distribution is sort of rounder, right? This distribution sort of looks like it's strictly convex. This one looks like it's concave down, and then there's an inflection point maybe, and it suddenly becomes concave up or convex over here. Let's keep on in this fashion, and I'll take samples of size. Let's go with a sample of size 5 maybe. Okay. Oops. There we go. And so now, then I'll put my sample means over here in column 6 and calculate row stats. Okay, and now let's make a histogram of those sample means. Okay, and of course we want to put them on the same scale with the others. So I'll go from 0 to 200. All right. So how does that compare to those other graphs? It's even rounder. You might even argue that it's has more of a bell shape to it. Okay. In fact, you know what? Let's go crazy here and let's take samples of size samples of size 30 maybe, or samples of, yeah, that's good. Samples of size 30. Okay. There we go. And so I'll put my sample means over here in column 31 and calculate row stats. Put in column 31 and we'll make a histogram of that. And of course we want to put it on the same scale. But hey, look at that. That looks kind of like a bell shape, doesn't it? Like a normal? Yep. That is the mathematical central limit theorem at work for us there. Whoa. It's kind of spiky though, isn't it? Okay, let's put these 4 plots where we can see them. So here we have samples of size 5. Oop, I mean by 5 I mean 30. Okay. All right. Yeah. So this is the central limit theorem at work for us. As our sample size increases, the sample mean tends to start clustering around the actual mean. Remember, the actual mean for this distribution is 25. 25. And sure enough, yeah, 25 is right in around here, if you can see that. Okay, and also the central limit theorem says that the standard deviation is going to, well, actually we don't need the central limit theorem for it, but the standard deviation of the sample mean is sigma over root n, and so in this case that turns out to be about right. You can figure that out. The n is 30, and what else does the central limit theorem say? Oh yeah, it says that the shape of this is going to start looking like a bell, right? Like a normal curve. And sure enough, it is. And why is it getting spiky like that? That's because the standard deviation is sigma over root n. So as the sample size goes up, sigma over root n goes down. It's starting to cluster. The sample means are starting to cluster in very tightly right in around the actual mean of the distribution. Okay, so that is that.